Transformation equations. Use transformation equations. What do we mean by transformation equation? By transformation equations, we mean that there are equations which connect the generalized coordinates and the coordinates that we are familiar with. Okay, the Cartesian coordinates, for instance. Okay, the equations connecting this are known as the transformation equations. Okay, so basically you'll write the kinetic energy as summation over I m I v I square. Okay, half divided by 2. Okay, this half mv square for one particle. So this is mi half mi vi square is the kinetic energy for the ith particle, and you have to sum over all the particles to get the kinetic energy. It's fairly simple. Okay, it's not like in Newton's case you have to look for all the forces and then resolve the forces into different components and then write down the forces, etc. Here you just take the kinetic energy of all the particles and add them up. Okay. All right, and then in the VI, in terms of generalized coordinates, this will become, you'll see this will become of this form. You can either use this or you can do it differently. These are vectors, okay, and there's a sum over I, all right. So this you may not have to immediately memorize this, or you may not have to immediately use this, but this is rather clear, I hope, because we need, what we need is Ri dot, okay, Ri dot, and we have written Ri as a function of generalized coordinates Qi. So it is just dou Ri by dou Q dot plus dou Ri by dou T. There's an explicit time dependence. So that part is fairly simple. Okay, so this is the general technique. Now let's go on to solving some of the problems. All right. The first, let's look at a single particle in space. Single particle in space. Okay. So before starting, just a moment, if in case my connection gets cut off, you have to wait for a couple of minutes so I can restart the system. Okay, I've got a generator and all that. So in case if I am lost for a couple of minutes, please don't leave. You just wait and I will be back. Okay, so let's talk about the single particle in space. We'll do it in Cartesian coordinates. Okay, first we'll do it in Cartesian coordinates. Cartesian coordinates is your usual XYZ coordinate system. Okay. So let's write it in this form so that we are sufficiently general. Okay, we'll take this form where T is the kinetic energy. Okay, why we are writing it in this form is because it may not always be, maybe all the forces are not derived from a potential, and then you can still use this form. Okay. Now, what is Qj? Let's first look at Qj. Qj, I said it's equal to, for the ith particle. We are dealing with a single particle in space, and there are no forces acting on it. So Qj, I mean, there are no constraints acting on it. It's just a single particle in space. Okay, it's free to move anywhere. So first, let's look at Qj. Okay, this is equal to, because there's only one particle, you don't have the summation. So it's F vector dot dou R vector by dou Qj. Okay, this is for the jth coordinate. All right, the jth generalized coordinate. You may have a number of generalized coordinates, and in this case, you are looking at Cartesian coordinates. So generalized coordinates are just x, y, and z. So this is equal to, yes, yeah, this is equal to F vector. So there are three components. This is a vector equation. There are three components. So let's write it as F vector. So for Q, let's write it as Qx. Okay, F vector dou R vector dot dou x. All right, and Qy would be F vector dou R vector by dou y, and Qz would be equal to F vector dou R vector by dou z. Okay, now what's this If you look at R vector, we usually write R vector, the position vector of the particle, as xi plus yj plus zk, right? So dou R by dou x is just I cap. Okay, so this is F vector dot I cap. This means that this is a projection of the force, or projection of the force vector in the I cap direction. Okay, so the question is, what's the component of F vector in the direction I cap? And we always write this as Fx. In other words, we write F vector as F dot I, Fxi plus Fyj plus Fz z cap, right, or k cap, right? And this could be any vector. Okay, this vector is something real that exists in space. Okay, we are just, what we do here is that we are just taking its components in a convenient coordinate system. Here it's the Cartesian coordinate system. That's all. Right? And similarly, in this case, this would be Fy and this would be Fz. Okay. So that takes care of the Qj part for single particle. If there are a number of particles, you have to add up all these terms. And here again, additions are just scalar additions. So it's much easier. We are just adding a scalar function. Okay, there are no vectors or components or anything of that sort. All right. Now let's look at the kinetic energy. We have got the right hand side. Let's have this term T is equal to half m. We can write it as x dot square plus y dot square plus z dot square. Okay, it's just v vector dot v vector. And then we need dot t by dou qj. Q1 we have taken as x. Okay, so here we have taken Q1 as x, Q2 as y, and Q3 as z. All right. So dot t by dou x dot. Okay, dot t by dou x dot is equal to, it's just m x dot. Okay, just take the derivative, and this 2 will get cancelled to mx dot. All right, so it's mx dot, and we need d by dt of dot t by dou x dot. That's just the time derivative of this, so it would be mx double dot. Okay, we can write the time derivative with a dot notation here, so it's mx double dot. Similarly, we'll get d by dt of dot t by dou y dot is equal to my double dot, and d by dt of dot t by dou z dot, that's equal to mz double dot. Okay. Now for each, so the important thing in the Lagrangian formulation is that for each of the coordinates, you have to write down an equation. You have to write an equation for x, you have to write an equation for y, and you have to write an equation for z. Okay. So let's look at the equation for x. Just substitute it here. We have everything here. And dou t by dou qj, it's equal to 0. There are no potentials. Okay. We'll also write that dou t by dou x equal to 0, etc. Okay, so that's the case for all of us. So just putting it in here, you see that for x, we get the equation of motion for x, that's equal to mx double dot is equal to fx, my double dot is equal to fy, mz double dot equal to fz. That's for, this is for x, this is for y, and this is for z. Okay, what are these? These are just Newton's equations in component form. So the Lagrangian formulation is equivalent. It gives you all the results that Newtonian equation gives. All right. And in the case of a single particle in free space, okay, the configuration space is the real three-dimensional space itself. Right? You need the three generalized coordinates we have chosen are x, y, and z, etc. Okay, I hope that's clear. So it's equivalent and sometimes, not sometimes, mostly more powerful, depending on what problem you need to solve. It's more powerful than Newton's formulation. It's simpler to use because we are dealing with scalar quantities. It's easier to generalize. Okay. And there are deep reasons why this kind of equation works. We will be coming to that. All right. Now let's take another example. Let's do the same thing in plane polar coordinates. I mean, this is important. Yeah, everything is important, but it's good to do this thing. Okay? Let's do the same thing in plane polar coordinates. Okay, Lagrange's equation in plane polar coordinates. Now, in plane polar coordinates, we have two coordinates. Suppose you are talking about a plane. Okay, you are talking about two-dimensional, the what do you say, the surface of this board or some surface. Okay. Now there's a particle here, or a point here, this space. We have the coordinate system here. Now, in order to locate this in a different coordinate system, we can use two numbers. Okay. One number is the distance from the origin. We call this as r. It's not r vector, it's just a distance. Okay. And then theta. All right. So if you have the theta is direction with respect to the x-axis, so to speak. So theta is here, and if you specify theta and r, the position of this particle, or any position in the space, is completely specified. Okay. Now we can easily look at the transformation equations. Let's do the whole step here, and then we'll interpret the result. We have the transformation equation. All right. What are the transformation equation? What's the x coordinate of the system? X coordinate is equal to, let's write it as x equal to r cos theta. Okay. And we have y is equal to r sin theta. Just by looking at it. R cos theta and r sin theta. Okay. So our generalized coordinates here are, okay, we have taken r and theta. Our generalized coordinates are, we can write this as qj is r comma theta. Right. Qj is r comma theta. Now we can find the kinetic energy. Right, we can find the kinetic energy. So for finding the kinetic energy, you just take half m x dot square plus y dot square. All right. So let's write it down here. T is equal to half m x dot square plus y dot square. All right. And you find x dot from here, it's minus. Yeah, let's just find x dot. Yeah. So we need to find x dot and y dot. You just take the time derivative, because r and theta both depend on time. We have to use what you call as a product rule or Leibniz rule. So this is r dot cos theta. Okay, x dot is equal to r dot cos theta minus r sin theta theta dot. Okay, so the sign minus sin theta theta dot is the derivative of cos theta with respect to time. Okay, so since the theta depends on time, we also have a theta dot over there. Okay. Similarly, y dot is equal to r dot sin theta. Okay, r dot sin theta plus r cos theta theta dot. Okay, just take the time derivative of x and y. Now, now we can find the kinetic energy. T is equal to half m x dot square plus y dot square. Okay, so just square these terms and add. Right, that's equal to. So if you square these terms and add, you will see that there are some cancellation. Okay, and cos square theta plus sin square theta is 1. You can use that. So you can just do it. All right, you just square these terms and add. Okay, and then you get this thing. This is equal to half m r square theta dot square plus r dot square. Right now, so you can do this. Okay, you can just square these terms and add. But the important thing is the intuition here. Right, see, r is a distance-like coordinate. Okay, it's a distance. R is a small distance. So r dot would be the velocity along that direction. Right, and r square theta dot square is the square of the angular velocity. Right. Sorry, sorry, theta dot square is the angular velocity. So r theta dot is the linear velocity corresponding to a small change in theta dot. But we'll see these things in detail. Okay. So thing is that always you may not have to write these equations. Okay? If you don't know, of course, you just write down the equations. But if you have a situation like this, you can just directly use this form. All right, because this is the radial part and this is the angular part. That's obvious. You can check the dimension. Theta alone is not a distance, so you cannot have theta dot alone as a velocity here. So it should be some sort of r theta dot or r d theta, etc. Right? Because r d theta is a distance. Okay. So we have the kinetic energy here. Now, what about the generalized force? What about the generalized force? So we'll do that also. The generalized force. Okay. So we can write Qj. Again, we are dealing with a single particle. So we will have just F vector dot dou r vector by dou qj. All right. If there are more particles, you would have to write the force on each particle and then sum over all the particles over here. This is for a single particle. All right. So we can now write this down. This is equal to f vector dot what's dou r vector by dou qj. So yeah, so for q we have two coordinates here, right? Q r and theta. So corresponding to that, you have to take q r and q theta, right? The generalized force in this there. So this is f vector dou r vector by dou r. Okay. And q theta f vector dot dou r vector by dou theta. Right. Now, how do we find this? How do we find this? In order to find this, you need to write r vector as a function of r and theta. Right? You have to write r vector as a function of r and theta. Let's see how we can do that. Okay. So you can write dr vector like this. In order to find r vector as a function of r and theta, you can write dr vector. Generally, can be written like this. This is equal to, let's say, infinitesimal displacement infinitesimal displacement in r cap direction. Okay, in r cap direction. So we are resolving the total displacement vector in terms of r cap direction and theta cap direction. All right. So there would be two components. One would be the infinitesimal displacement along the r cap direction, and the other one would be the infinitesimal displacement along the theta cap direction. Okay. So the unit vector is r cap along. All right. Or the and then you will have similarly infinitesimal displacement in theta direction multiplied by theta cap. Okay, that would be dr vector. Now, how do we find that? Okay, how do we find that? Right. So what we do is that we just draw it. Okay, x, y. So we need to talk about some sort of displacement. Okay, in the r direction, it's obvious because this is the r cap direction. Right, this is r cap direction. So any movement in that direction is infinitesimal displacement in r cap direction. So you can simply write it as dr. So what about this term? Okay, this is simply not theta dot. So let's check. Okay, so this is the theta direction. This is the theta direction. So we can write this as d theta. I hope it's visible. Let's see. All right, just draw a bigger. So we have got the initial position of the particle here, and at after an infinitesimal time, we have the particle here, and then it has gone by an angle d theta. All right. So we need to draw here, and this distance is r, so this would be r d theta. Okay, so this is the theta direction. All right, this is the r cap direction, and this is the theta cap direction. All right, so this is the displacement in the theta cap direction. So I said this is the theta cap direction. The displacement theta cap direction is r d theta. Okay, so from this we can write dr vector is equal to dr r cap, okay, plus r d theta theta cap. Okay, r d theta cap. Now, if you look at this already has the dimension of length. Okay, so we can simply write d theta, dr. But d theta does not have a dimension of length. You need a quantity here which has the dimension of length. Okay, and you'll see that r d theta has the dimensions of length. So this is correct because this term has dimensions of length if you take the magnitude. All right. Now we can also write by the chain rule. Okay, because r is a vector function of r and theta, we can write this thing as dr vector of r comma theta as, you just use the chain rule. This you can write it as equation 1. Okay, so dr vector of r comma theta, you can write it as dou r vector by dou r. Okay, in the direction r, this is dr, plus, remember this is a vector and this is a scalar. Okay, so we have to be very careful about the vector sign. So this is dou r vector by dou theta d theta. This is just the chain rule from partial differentiation. Okay, if you have function of r and theta, x and y, df is equal to dou f by dou x into dx plus dou f by dou y into dy. Okay, we have used the same thing. Now, if you compare these two equations, you can take the coefficients of dr, okay, and d theta. You can equate the coefficients of d theta. So, equating the coefficients of dr, you see that dou r vector by dou r, this is simply is equal to r cap. Okay, just equate the coefficients of dr, and similarly, you see that dou r vector by dou theta is equal to, you equate the coefficients of d theta, and you see that this is equal to r theta cap. Okay. All right. Now we want to find generally. You have all you need. The QR is equal to f dot dou r vector by dou r, right? So I'm continuing here. QR is equal to, what we have found so far is just this, dou r vector by dou r and dou r vector by dou theta. Now just take the scalar out. Okay? QR is equal to f vector dot dou r vector by dou r was r cap. Okay, so this means that you are resolving the force, okay, the real vector that exists in space, you are resolving it in the direction r cap. Okay, so it's just taking scalar product r cap. You can say that you are projecting this vector along the r cap direction. And this you can write simply as the component of force in the r cap direction. We can just give the notation as FR, right? What about Q theta, the generalized force in this case? It's equal to F vector dot, what was dou r vector by dou theta? It's r theta cap, okay? It's r theta cap. So F dot theta cap is just the component of force along the theta cap direction. So this simply you can write it as r f theta. You can write it as r f theta. All right. Now you already you have all the equations. We have FR, we have the generalized forces, we have the kinetic energy on the left hand side. So now we just write the equation of motion. All right. Just write down the equation of motion. Did we find the derivatives? No. Okay, let's, so we have everything now. So we already had T is equal to half M R square theta dot square plus R dot square. All right. So we have the generalized forces here. Now, what's the equation for R? Okay, for the R coordinate. We have one equation for each coordinate, as I told you. In this case, our coordinates are R and theta. Let's find the equation for coordinate R. All right. So we can write this as d by dt of dot t by dou r dot, okay, minus dot t by dou r is equal to qr. Okay, this is the equation for r. Now what's dot t by dou r dot from here? You see that this is equal to d by dt of dot t by dou r dot is just, okay, it's just mr dot. Okay, and we also have minus dot t by dou r. Remember that there's a function of r here. Okay, so it's not zero as in the previous. So you have to take care of this. So dot t by dou r is equal to, it's m r theta dot square, right? So we have d by dt of dot t by dou r dot, that's d by dt of mr dot minus mr theta dot square. Why mr theta dot square? Because you take the derivative with respect to r here, right? So there's a square here, it comes here. Yeah, the derivative of x square is 2x, etc. Okay, so minus mr theta dot square is equal to qr. What was qr? It's fr. All right, and taking the derivative here, you see that, and then you can rearrange mr double dot. Okay, mr double dot is equal to, or we can write it in two ways. So let's write it like this: mr double dot minus mr theta dot square is equal to fr. All right. Now this looks very much like Newton's equation. Okay, you have got mr double dot mass multiplied by acceleration is equal to force, but there's an extra term here. All right. This term is called the centrifugal acceleration. the centrifugal acceleration. So either we can call this as a centrifugal acceleration, or we can write it as mr double dot is equal to fr plus mr theta dot square. In this case, this would be the centrifugal force. Okay, r theta dot square is the centrifugal acceleration. Okay. So this is a good thing. This shows that the Newton's equation doesn't have exactly the same form in plane polar coordinates. Okay, in Cartesian coordinates we would have mx double dot is equal to fx. That's all, right? But when you go to coordinates, plane polar coordinates, you see that the form of the Newton's equation changes. And usually in classical mechanics, we call this as fictitious forces, right? Because we are in a different kind of coordinate system. And we use this plane polar coordinates in system where we have some sort of rotational symmetry and all that. Okay, so that's one equation. Now, what about the equation for theta? Let's write the equation for theta. Right, equation for theta. So that would be d by dt dot t by dot theta dot minus dot t by dot theta. That's equal to q theta. All right, q theta we have already found. So d by dt of what's dot t by dot theta dot? You have a theta dot only here. You just take a derivative with respect to theta dot. You see that